Hello, I'm Eric Pearson. I'll be talking about some research I've been doing at the University of Michigan under Professor Brian Kiedraski for my master's degree, the prediction of neutral particle analog Monte Carlo computational time with discrete ordinates. A little bit of a mouthful. Some general introduction before we dive into things. As you probably know, Monte Carlo particle transport can be used to find high fidelity results with a few approximations, which is why it's desirable. However, because of statistical uncertainty, it may take a large number of samples to get reasonably converged answers, which can take a long runtime. The figure of merit for a Monte Carlo simulation is typically 1 over r squared t, where r is the relative error associated with estimates of interest, and t is the total simulation runtime. There's been a number of variance reduction techniques developed in an attempt to maximize the figure of merit. However, most of these techniques require non-trivial user-defined parameters. The current state of practice to get these parameters are hybrid calculations, wherein you first find the adjoint function deterministically, and then you use that adjoint function to generate weight window bounds using an approach like consistent adjoint-driven importance sampling, or CADIS. This approach has been shown to be very successful. However, there is an issue in the CADIS approach where if particles are leaving a region of low importance and entering a region of higher importance, in an attempt to capture that region more accurately, particles will split, sometimes very much so, resulting in an overall negative impact of figure of merit because the time it takes to simulate all those particles um, overwhelms the amount of reduction you get in the relative error. So the overall figure of merit is decreased, and this issue is known as oversplitting. You may also be familiar with FWCADIS, a similar approach, which also suffers from oversplitting. In this work, we're going to attempt to improve the CADIS approach in the following ways. First, we want to find the expected future time field. This field tells you, given a particle at a certain point in phase space, how long do you expect the Monte Carlo simulation to take to simulate that particle to the end of its history? That is the expected future time field. And you get that by solving the future time equations, which we'll talk about a lot more next. Ideally, and then the goal is to use the expected future time field to mitigate the oversplitting problem in CADIS, and we'll talk about how you do that later. If successful, we'll end up with improved variance reduction parameters, which generate shorter runtimes and reduced uncertainties in Monte Carlo simulations. This is relevant to the NNSA mission because it's accelerating Monte Carlo particle transport. The goal is to automate this process as well, so you eliminate the need for expert judgment in your optimal variance reduction parameter generation, so you get reduced runtimes without that expert judgment, which will allow Monte Carlo to be applied to a wider set of problems more readily. An overview of the technical approach we took for this work. First, we derived the future time equations for the non-multiplying analog case. And what you end up with is something that looks like an adjoint neutron transport equation with special source terms, which you'll see later. These source terms for the future time equation are estimated using embedded timers in the University of Michigan's Hammer code. And then with those source terms, the future time equation can be solved in the Hammer code's 2D discrete ordinate solver. And then the goal, as stated before, is to use the solution of future time equations, the expected future time field, as a heuristic in weight window bound generation for optimal Monte Carlo simulation. The role of the Hammer code, I'll go into this a little bit because you may not be familiar with the Hammer code. It's a student-driven particle framework. It has both Monte Carlo and deterministic capabilities. The goal of this code was to be a testbed for advanced hybrid deterministic Monte Carlo methods, which is what it is. It's very useful in this work because we need the Monte Carlo side to implement embedded timers to get source terms for the future time equation, and we need the deterministic side to then solve the future time equation. And ideally, we would then use that solution to generate optimal variance reduction parameters and turn that back to the Monte Carlo side for an optimized simulation. So for the analog non-multiplying case, what's going on in a Monte Carlo computational cell? So starting at some arbitrary phase space P here, some position, direction, and energy, particles stream along their path until they collide or cross the surface of the cell they're in. So what we see here is a collision, moving to phase space P1, where a collision occurs, which then can result for the non-multiplying case in either an absorption or a scatter. So for an absorption, the history is over and it's terminated. That's noted by the red phase space P2, or the particle can scatter and continue on in simulation, which is noted by the blue phase space P3. or the particle cannot collide in its current cell and continue on all the way to the edge of the surface, phase space P4, and then cross that surface in a phase space P5. Importantly, where the computer is actually doing processing and consuming computational time are at surface crossing events and collision events. So the equations governing the future time of the system consider these collision events, and it looks like this. So here's the future time equation, and you'll notice it looks a lot like the adjoint neutron transport equation with different source terms. So this first source term here is the total cross-section times these two tau with some subscript terms. These terms represent the amount of computational time required to process a collision event. And then down below, we have some prescribed function on the boundary of the surface, plus the time it takes to cross the surface, which is denoted by these tau with some subscript terms. In the typical adjoint problem, what you may be used to seeing is tracing back in time from responsive interest, like an interaction in a detector. So you'll take particles that interact in a detector and back them out through time to get the relative importance of different points in phase space to that detector response. For the future time equations, it's still an adjoint problem, but the response we care about now is the time consumed in the Monte Carlo simulation. So we're starting at points where time is consumed in the Monte Carlo simulation and backing them out to find the expected future time at different points in phase space. So you can imagine it as taking these surface crossing points and collision points and sucking them back up in time to find the expected future time at some point in phase space P. The source terms for the future time equation are physically the computational time required to process a transport event. So to process something like a collision event or surface crossing event, how much time does that take in seconds by the computer? That is the source term of the future time equation. So because it's the time it takes for a computer to do something, and because what happens at collision events and surface crossing events can change depending on the problem. So if you have like different tallying going on, or in the non-analog case, different variance reduction going on, source terms are problem dependent. And because not all computers are created equal, they're also machine dependent. So the way we estimate them in this work is using timing routines that wrap around the transport routines and simply start and stop before and after that transport routine takes place. And then we can get an estimate of how long it takes to perform that transport routine. However, having these timing routines embedded in the source code of the Monte Carlo transport itself, you're changing how the computer's working. So you're adding inherent error to your timing sources, which we'll touch on later. What it looks like is to have a short timed Monte Carlo simulation where we then generate the source terms for the future time equation. We can then solve the future time equation in the discrete ordinate side of the code. And we have the existing capability of doing an adjoint solution in the discrete ordinate side of the code. And then together with the adjoint function and the future time equation solution, we're hoping to find more optimal variance reduction parameters for then an optimized Monte Carlo simulation. So here's what the future time equation solution looks like. We have a 10 by 10 mean free path system with homogeneous 80% scattering, 20% absorbing material. On the left here, we see cell IDs. So you can see there's 5 cells separated by cylindrical surfaces, but because the system is homogeneous, those surfaces aren't doing anything besides taking computational time. And then on the right here is the future time equation solution. So this is the expected future time field. And what it tells us is if you plop a particle down at some point in the system, how long do you expect the Monte Carlo simulation to take to simulate that particle to the end of its history? So if I can get a laser pointer here, if you were to plop a particle down here towards the center of the system and where it's hotter, it would take the particle more time comparatively to the edge of the system because it's going to ping pong around in a mostly scattering material, which takes computational time. Additionally, if you pop a particle near a surface, it's likely to cross that surface, which again takes computational time. So it makes sense that the expected future time field is hotter towards these surfaces. If you take the inner product of the expected future time field with the source intensity, you end up with an estimate of how long the Monte Carlo simulation will take on average for history. And that's what we've been using to check the accuracy of our results. So for most test cases, errors are typically within 10 and 30% of what's estimated versus what's observed. Finding the observed time for history is very simple. Just run the Monte Carlo simulation. And then for the above here, this is a 28% error case. Those errors are pretty high, but what's important for branch direction optimization isn't the magnitude of the future time equation solution, it's the shape, because we want to have the ratio of neighboring regions accurate so that when we take that ratio, we end up with the correct result and constant terms will drop out. So in this work, we've shown that you can derive the future time equations for an arbitrary Monte Carlo implementation, in this case, the hammer code. We've shown that embedded timers can be used to estimate the future time equation source terms. And we've also shown that the future time equation can then be solved using the discrete ordinate solver with slight modifications. The goal then having the solution to the future time equation, the expected future time field, is to use it as a heuristic to improve the Cadis approach for variance reduction parameter generation. So two ways we're thinking about doing that, but have not yet done, is one, changing the terms in the solution to the adjoint system to keep particles away from high cost regions of the problem. So using the information about what regions of the problem take more computational time to simulate, we will discourage particles from going to those regions when we're solving for the adjoint function. And then that adjoint function can be used typically in the Cadis approach to get weight window bounds. And hopefully that'll be more optimal. Another way we're thinking about doing this is setting a cap on how much splitting you can have in the Cadis approach between regions, which is already done. But we think we can then use the future time equation to quantitatively inform what that cap should be. So looking at how much computational time is being consumed region to region, we can make a more educated guess about how much we should be splitting between those two regions. And then ideally, with improvement to the Cadis technique, we'll end up with, again, more optimal variance reduction parameters, which will lead to a Monte Carlo simulation that is shorter and gets better accuracy. This work was performed in collaboration with Los Alamos National Lab Monte Carlo Codes Group scientist Joel Coleza. After I graduate this year with my master's, I plan on doing another remote internship with that group, XCP3. And everything we've presented here, the future time equation solver approach to improving Monte Carlo simulation is general. It's currently implemented in the Hammer code, but it can be incorporated into other hybrid codes to accelerate Monte Carlo simulation. The goals of this work were to first derive the future time equation for the non-multiplying analog case, and then implement embedded timers to estimate the source terms for the future time equation. And with those source terms, then solve the future time equation using a discrete ordinance method. Those first three have been accomplished. The fourth, as we've talked about before, is to use that solution as a heuristic for weight window parameter generation. If that is successful, then we'll have a new to-be automated approach for general purpose Monte Carlo optimization, which would improve the speed and accuracy of results from Monte Carlo simulation. Next steps in this work are to implement the Cadis weight window bound generation approach in Hammer so that we can then use the future time equation solution, which we already have, to improve the weight window, or the Cadis approach for weight window generation. Those approaches, as we've discussed before, are to inform maximal splitting parameters across regions, then maybe to augment the total cross section to discourage particles entering high cost regions. We would then need to fully test the automated workflow for more general problems and ideally extend the discrete ordinance solver to 3D so we could solve more interesting problems. Thank you for listening. I'd like to acknowledge the Consortium Monitoring Technology and Verification. Thank NSA and DOE for their support.